Hello everyone, welcome to my lecture. Here we have a discussion about sequences and its convergence. Yes, first let's see the definition of sequence. You can see the definition of sequence here, definition number 1. Let X be any non-empty set. A sequence in X is a function S from n to X, where n is a set of all natural numbers. Okay, such a function is known as a sequence in our set X. Okay, a function from natural numbers to that set X. Okay, denoted as S. That is an example of sequence. Next, you can see below that value of the function S at n is denoted as xn. Okay, usually suppose you have a function f of x. Okay, so suppose you have a function f, you denote it as f of x. Okay, if it is a function from natural numbers, you can denote it as f of n. Okay, here this function is named as s. Okay, but instead of denoting it as s of n, we denote it as xn. Okay, the first term of that sequence, the first image is denoted as x1, second one is denoted as x2, third one is denoted as x3, and so on. Okay, next point. Next point, the sequence itself is denoted as this one. Okay, this means sequence xn. In this, all the terms of this sequence are included. Okay, x1, x2, x3, etc. all are included in this. Okay, that sequence completely is denoted as this symbol. Okay, sequence xn. Okay, yes. So that is the definition of sequence. Next, I will show you one example. Two examples for a sequence you can see here. Okay, two examples for a sequence. Look at the first example. You have a sequence 1 by n, ordered pair 1 by n, 1 by n. N belongs to n, natural numbers. This is a sequence in R2, R cross R. Okay, this is a sequence in R2, R cross R. Okay, what are the elements of the sequence? What are the terms of the sequence? These are given here. Okay, when n is 1, okay, n belongs to natural numbers. When n is 1, this becomes 1 by 1, 1 by 1. That means 1, 1, ordered pair 1, 1. Okay, when n is 2, this becomes 1 by 2, 1 by 2. That means ordered pair 1 by 2, 1 by 2, second one. When n is 3, this becomes ordered pair 1 by 3, 1 by 3, and so on. Okay, these are the elements, or these are the terms of this sequence. This is an example of a sequence. Okay, it is a sequence in R2, R cross R. Next one, next example, yes. Ordered pair n, n square, n cube. N belongs to natural numbers. This is another example of a sequence in R3. Okay, R cross R cross R. These are ordered triplets. Okay, these are ordered triplets because this is in R3, R cross R cross R. When n is 1, what will happen here? This becomes 1, 1 square, 1 cube. 1 square and 1 cube both are 1 only. So you will get 1, 1, 1. That is what you can see here. Next, when you put n as 2, the second natural number, this becomes 2, 2 square, 2 cube. 2, 2 square, 2 square is 4 and 2 cube is 8. So 2, 4, 8. Okay, 2, 4, 8. When n is 3, this becomes 3, 3 square, 3 cube. 3 square is 9, 3 cube is 27. Okay, so 3, 9, 27 and so on. You will get all the elements of, you will get all the terms of this sequence like this. All right. Yes. Next is convergence of a sequence. Okay, convergence of a sequence. Now we discussed about sequence. We have an introduction about sequence. Next topic is convergence of a sequence. Okay, what is mean by convergence of a sequence? You can see the definition here. Definition number 2. Okay, definition number 2. definition number 2, convergence of a sequence. Okay, see, let this xn, okay, sequence xn be a sequence in a metric space xd, okay, a set x with a metric d, and x be an element of that metric space capital X. We say that this sequence xn converges to that small letter x in capital X if given any epsilon greater than 0, there is a positive integer m depending on that epsilon, such that d of xn x, I mean the distance between that xn and our x in capital X, will be less than epsilon for all n greater than or equal to that particular m. Okay, if this is happening, we can say that this sequence is convergent sequence, that is converging to this x. Okay, let me repeat it. Suppose we have a sequence xn in a metric space capital XT. Okay, and this x is an element of that capital X in that metric space. Okay, now when can we say that this sequence xn converges to that x in capital X? We can say if given any epsilon greater than 0. Okay, for any epsilon greater than 0, you should find a positive integer m that will depend on that epsilon which you have taken there, such that this will happen. Okay, for all the natural numbers greater than or equal to that m, distance between that xn and x will be lesser than epsilon. This will happen if you take any epsilon. Okay, whatever small that epsilon can be, it can be 0.1, it can be 0.001. If epsilon is 0.1, you will find an m there, such that this will happen. If epsilon is 0.01, again, then also you will find another m there, such that this will happen. If epsilon is 0.0001, for any positive epsilon, you can always find a positive integer m. When n is greater than that m, this thing will happen. The distance between all the elements of that sequence, all the terms of that sequence and that particular x will be lesser than that epsilon. Okay. Now this is the definition of converging sequences. I hope it's clear. Next, you can see some examples. Okay, one example for converging sequence. Yes. Example, consider the sequence. Okay, we have taken this as an example for sequence. Okay, after defining the sequence. Okay, the same example, the same sequence, ordered pair 1 by n, 1 by n. N belongs to natural numbers. This is a sequence in R2. Okay, R cross R. Now we are taking the metric, the standard metric here, okay, or the usual metric, the usual distance, the distance between 2 points in R2. We know that is root of x2 minus x1 the whole square plus y2 minus y1 the whole square. That is the distance between 2 points in R2, right? x1 y1 comma x2 y2. We are taking the same distance, okay, the standard metric or the usual metric d. Okay, and we can say that this particular sequence, okay, this sequence in R square with standard metric d or the usual distance will converge to which point? Will converge to 0 0, ordered pair 0 0. Okay, I will show that, I will prove that here. See, here we have the proof. Okay, to prove that, what we need, for any epsilon greater than 0, you have to find a positive integer m, such that this will happen. When for all the natural numbers greater than or equal to that particular m, the distance between the terms of that sequence and that particular x to which it is converging will be lesser than epsilon. This will happen. Okay. Yes. Suppose that epsilon greater than 0 is given. Okay. Let epsilon greater than 0 be any positive number. Okay. It's an arbitrary positive number, arbitrary positive real number. Okay. We will prove for this epsilon greater than 0. Since it is arbitrary, it is true, it will be true for any epsilon greater than 0. Okay, it is true for any real number. Okay, so that's why we are proving it for arbitrary epsilon greater than 0. Okay, yes, let epsilon greater than 0 be given. What we need to find here? We need to find a positive integer m, such that if the distance between xn and that x, here xn, the terms of our sequence is 1 by n, 1 by n. Okay. And our x, the point to which our sequence is converged is 0, comma 0. Okay. Yes. So instead of this xn, we have that 1 by n, comma 1 by n, ordered pair 1 by n, 1 by n. And instead of this, we have 0, 0. Okay, here this xn is converging to x. Here this 1 by n comma 1 by n is converging to 0 comma 0. Okay, so this is simply distance between xn and x only. Okay, yes, it will be lesser than this epsilon, the epsilon that we have taken here. Okay, for all n greater than or equal to that particular positive integer m. Okay, yes, you have to prove this. This will happen. Okay, this will happen if you take any positive epsilon. This will happen if you take epsilon as any positive real number. You will always find a positive integer m such that this thing will happen. Okay, let's see. First of all, what is the distance between 1 by n and 0 comma 0? Sorry, 1 by n, 1 by n and 0 comma 0. I told you already that this is the usual metric. So the distance between them is root of x2 minus x1 the whole square plus y2 minus y1 the whole square. Okay. That's why root of 1 by n minus 0 the whole square plus 1 by n minus 0 the whole square. Okay. Well, this becomes 1 by n square. This also becomes 1 by n square. 1 by n square plus 1 by n square becomes 2 by n square. Okay. So that means root 2 by n. Okay. Root of 2 by n square means root 2 by n. This is the distance between that 1 by n, 1 by n and 0 comma 0. Okay. Suppose this equation is equation number 1. Okay. Next one. Now, for this epsilon, what we need to find? Okay. One epsilon greater than 0 is given. We need to find a positive integer m. Right. We need to find a positive integer m. Okay. That is our next aim. So that this inequality will happen. Okay. This inequality will happen. So we need to find a positive integer m for this particular epsilon greater than 0. Okay. Yes. Now, don't worry. We have an m here. Okay. Choose m that is greater than root 2 by epsilon. We can choose easily, right? Because root 2 is a positive real number. Okay, epsilon is also a positive real number. That epsilon greater than 0 is given. Okay, epsilon greater than 0 is given. So root 2 by epsilon. Root 2 is a positive real number. Epsilon is also a positive real number. Whatever may be the value of this epsilon. Epsilon can take any positive real number. Okay. So if you fix that epsilon is a positive real number. So what about root 2 by epsilon? That is another positive real number because both root 2 and epsilon are both are positive. So root 2 by epsilon is another positive real number. Okay, another positive real number. Now if you have any real number, if you have any positive real number, you can always find a natural number greater than that one, right? You can always find a positive integer greater than that one, right? Suppose you have a real number 10,000.1204. You can find a positive integer greater than that 10,001, right? Suppose you have a real number 1,25,000.12730, a positive real number. You can take a positive integer greater than that. Okay, for example, 25 lakh. That is a positive integer greater than this number. Okay, if you have a positive real number 1 crore point 12865, you can select a positive integer greater than that 11 crore. So any positive real number you have. Okay, this root 2 by epsilon can take any real number, any positive real number. You can always choose a positive integer that is greater than this one. That is possible, right? So that's what we are doing here. We will choose this m. Okay, we will choose this positive integer and m as an integer greater than root 2 by epsilon. Okay, such an integer we are choosing. Okay, now if m is greater than root 2 by epsilon, what will happen here? We can say that root 2 by epsilon is less than m. Okay, m is greater than root 2 by epsilon means root 2 by epsilon is lesser than m. Okay, now cross multiply here, both are positive. Okay, epsilon is positive, m is also positive. So take this epsilon here and take this m here. So this becomes root 2 by m lesser than epsilon. Okay, root 2 by m lesser than epsilon. Suppose this is inequality number 2. Okay, inequality statement number 2. Okay, inequality number 2. Now, suppose n greater than or equal to m. Okay, this we can assume n greater than or equal to m. Why? We need to prove, see, we need to prove this inequality. We need to prove this inequality for all n greater than or equal to m. So this n greater than or equal to m we can assume. If only if this happens, then only this inequality happens. Okay, so this thing you can assume. So that's what we are doing here. We are assuming n greater than or equal to that particular m. This m we have already chosen here. Okay, what is m? M is a positive integer greater than root 2 by epsilon. Okay, such an m we have, and suppose n greater than or equal to m. Okay, if n is greater than or equal to m, then the reciprocal of n will be lesser than or equal to reciprocal of m. Right? If n is greater than or equal to m, then 1 by n will be lesser than or equal to 1 by m. Next, multiply root 2 on both sides. That means root 2 by n lesser than or equal to root 2 by m. Okay, root 2 by n lesser than or equal to root 2 by m. Now, we know from inequality number 2. Okay, what we have from inequality number 2? See here, this is inequality number 2. From inequality number 2, we know that root 2 by m is less than epsilon. What about from inequality number 3? From inequality number 3, we have root 2 by n lesser than or equal to root 2 by m. And this root 2 by m is lesser than or equal to what? Sorry, this root 2 by m is less than epsilon. Okay, so root 2 by n less than or equal to root 2 by m. That root 2 by m is less than or equal to epsilon. So by combining equation 2 and 3, this root 2 by n will be lesser than epsilon. That's what you can see in the next inequality. Okay, root 2 by n lesser than epsilon. This will happen if you combine inequality number 2 and 3. Okay, root 2 by n lesser than epsilon. Next, what is this root 2 by n? What is this root 2 by n? The root 2 by n is nothing but, according to equation 1, root 2 by n is what? Root 2 by n is distance between 1 by n, 1 by n and 0, 0. Okay, the distance between 1 by n, 1 by n and 0, 0. That is root 2 by n. Okay, so from equation number 1, instead of this root 2 by n, what you can write? You can write distance between 1 by n, 1 by n and 0, 0. If root 2 by n is less than epsilon, sorry, yes. If root 2 by n is less than epsilon, then d of ordered pair 1 by n, 1 by n, comma 0, 0 will be lesser than epsilon. The distance between the 1 by n, comma 1 by n and 0, 0 is lesser than epsilon. That means d of xn, x is less than epsilon, because xn is this one, 1 by n, 1 by n, and x is this one, 0, 0. Okay, so this inequality is proved now. Okay, so this will happen when n is greater than or equal to n. Okay, that is the definition of convergence sequence. Okay, that is the definition of convergence sequence. For all n greater than or equal to m, this inequality will happen. Okay, yes, I hope it's clear. Thanks for watching. Bye bye.